Okay, hey class. So now we're going to go on into some second order differential equations. And we're going to, just as before, we'll get them like slightly more complicated as we go. So the first one is kind of like the y prime equals ky example. This one's specifically set up to be like a spring. And we'll see that the next version that I do is a generalization of this one directly. So here if we have y prime equals minus ky, you can see a particular, so one thing is this, right? So again, we have a second order differential equation. This is generally going to need two parameters. We're going to have a space of dimension 2 in terms of solutions here, right? So if we could find two linearly independent solutions, we should be able to put them together as a linear combination of those two and get an arbitrary solution for this. So there's a little bit of linear algebra stuff going on in the background here. It's easy to see a couple of solutions here. So one easy solution is y equals sine square root of kt, and then y2 equals cosine square root of kt. Right? And that's because when you take the derivative of sine twice, you get back to sine, but with a minus sign. This square root of k comes out twice, so it becomes k, right? And so that's pretty clear. Same thing with cosine, right? They're kind of similar like that. And so the general solution would be alpha sine square root of kt plus beta cosine square root of kt. Whoops. Okay. Okay, so that's going to be this is going to be the general solution. It's going to have two parameters, right? So it'll be sort of a two-dimensional set of solutions. And later we'll see that this, we can generalize these solutions as sort of e to the I square root of kt. We'll see that in just a minute when I do the next set. Okay, good. So the particular example we have here is a spring, and so maybe if some of you have seen some physics, this is Hooke's law looking thing here. So we have a spring attached to a mass, and it oscillates with no horizontal friction, and the displacement y of t satisfies this Hooke's law. And let's see, so the mass is initially, so this is our initial conditions, right? It's initially displaced 5 centimeters from equilibrium and released from rest. And the frequency is going to be 2 oscillations per second. Okay, and we want an explicit formula for y of t, and then you want to determine the position of the spring after 0.3 seconds, right? So, so the way this is set up is sort of a spring attached like to a wall here, right? And there's some mass, we're ignoring friction, we're pulling it back a little bit, right? 5 centimeters. Okay, and we know its frequency, which we're going to call omega, is 2 oscillations per second, which is 2 hertz is the units that you have there. Okay, good. All right, and then we're just going to use the fact that we have this formula up here for solving it. Okay, so this is a little bit different than what we were doing before, where I was kind of doing a separation of variables to come up with a solution. Here we just kind of know the solutions look like this. I'll put a little bit more theory to that in just a minute. Okay, so one thing is that the frequency, right, is 1 over the period, right? And the period of this thing here, so the period of like sine square root of kt, well, the period of sine t is 2 pi, right? And so the period of sine ct is 2 pi over c, right? Because you kind of do the inverse, you contract by a factor of c, right? So the period here is 2 pi over square root of k, right? And so here we're getting 2 is 1 over that, so square root of k over 2 pi, right? And so square root of k is 4 pi. Okay, so k is equal to 16 pi squared. All right, so that's our k, and then we just have to find alpha and beta. All right, so this one's pretty straightforward. So we have here, let's see, what do I have here? Yep, just that, right? So y double, here's our final system, right? Y double prime is minus 16 pi squared y, y of 0 equals 5. That's the initial position. It starts at rest. Y prime of 0, right, is equal to 0, right? So this is the initial conditions right there, right? So this is the initial value problem, right? And those are the initial conditions, and we need two initial conditions to get a unique solution here, right? All right, and so we look at this and we get that y equals, remember it was alpha square root of k, so that's the 4 pi, right? So sine 4 pi t plus beta cosine 4 pi t, right? And you have y of 0 equal to 0, right? So that's alpha, sine 4 pi times 0, which is just sine 0, which is, cosine, I want the cosine here. Beta, right? So beta cosine 0, which is 1, so beta, right? Whoops. So beta equals 0, all right? So we're going to say, 5. Beta equals 5. This is 5. Beta equals 5, right? And then we have that y prime of 0, right, is alpha 4 pi cosine 4 pi t plus, minus, right, because we're going to take the derivative of cosine and get a negative sign there, right? So minus 4 pi beta sine t, sine 4 pi t. All right, we plug in 0 there. Now that is 0, right? So that's what I was saying before. So we have 0 equals, right, this is going to become 1. So alpha times 4 pi. All right, so alpha is 0. Okay. So the final model is just y equals 5 cosine 4 pi t, right? That's our final model there. Okay, so that was a pretty easy one. All right, the next one will be a little bit more subtle compared to that one. Okay, now we're going to go on to a more general second order. These are second order linear differential equations, right? So linear because this is a, what do we mean by, like, if I have a linear combination of three things? So let's say I have x, y, and z, right? And I have a linear combination of these. So like 5x plus 3y minus 4z, right? That's a linear combination because I have just constants here, scalars, right? And then the x, y, and z, right? So here the thing we're combining are y double prime, y prime, and y. Those are like the x, y, and z up there, right? And it's a linear combination because it's 5 y double prime. An example, right? Plus 3y minus 4, y prime minus 4y, right? That would be a linear combination of y double prime, y prime, and y. And actually here the variable's y, so in some sense we even say that if these are functions of t, right? So g of t, right? So these kind of become like the scalars here because we're actually solving for functions. Y double prime plus, let's say, let's say f of t, and we'll see examples like this later. Y prime, minus 4. Sorry, I keep using. Let me clear all this stuff up. Okay, so let's say f of t, y prime minus k or plus k of t, y, right? So this would also be a linear, and then equal to something, equal to I don't know, L of t. That would be a linear second order differential equation too, right? So here I have constant coefficients, right? So, and maybe this is equal to, I don't know, 5 or something. But this, in fact, we don't need that. This could be a function, but these are constant coefficients, right? So that's the sort of setting we're interested in, right? And actually I'm interested in here only in solving this for homogeneous systems. So actually here we'll have 0 here. And I guess same thing here. Here we'd have 0 here. So homogeneous means that we have 0, right? We're saying it equal to 0. More general cases where we have a non-zero thing here, And to solve those, you would do what we're going to do next, but then you would also have to find a specific solution for that one case, right? And that's usually a bag of tricks, right? So I don't want to go too deep into the bag of tricks here. Anyway, the way to do this, so let's fix one. We can always, in this case, factor out the 5 and kind of reduce this sum, right? So we can always assume it has this kind of form. And for some reason, I called that a C in my notes. I'll just call it a P here. I don't think it matters. Equals 0, right? So again, that's the homogeneous part. These are both elements of R, right? So that's the constant coefficient part. Those are the coefficients. Whoops, and I need a Y there, right? So this is a linear combination of Y double prime, Y prime, and Y, right? Second order because that's a second derivative. What I'm going to do next with the systems later, we could take care of like third order, fourth order, etc., right? And the same kind of thing we're doing here can also be used for that. And so we'll actually redo this in two different ways, right? So one thing is here, I'm going to introduce this notation. So d something is like the differential operation. So dy is y prime. Right? I just want to introduce this for some notation here. So what we can do is instead of doing this like this, I can say this is d squared plus alpha d plus beta, and then kind of the identity map, right? So where we just don't do anything. I'll just call it beta. I'll just call it b, right? It's kind of an identity. So this is like an operator, right? It's taking y to y prime. This is going to be like the identity operator. I'll just put an I here, right? So it would take y to y, right? It's not doing anything. And so when I act on this by y, and by the way, like d to the 0, right, is like 1, right? So d to the 0 would be I, right? And this is equal to 0, right? So we have a situation like that. And then what I can do is I can look for the case, right, where that is actually equal to 0, right? So that's kind of the thought process here, right? So we're going to look at where that is equal to 0, and then we'll try to solve this thing, okay? So basically this is giving us a quadratic, right? So the quadratic is giving us this d squared plus alpha d plus b, or if you like, we can just call it over here. It doesn't matter what variables we use. I could use like x squared plus ax plus b, right? It doesn't matter what I call the thing, right? We just have this sort of quadratic, and then we can solve this quadratic, by factoring or by using the quadratic formula or something like that. And we'll use this in our solutions, right? Okay. So here, let's say that this thing factored into d minus lambda 1 and d minus lambda 2. So let's say we factored that. I'll keep using this notation. This sort of looks like eigenvalues, and that's what it's going to be later on. And so I have this happening equals 0, right? And then again, a little bit of theory. So the only way that these product of two things can give me a 0 is if one of the two products is 0. So I have d minus lambda 1 of y equals 0. I mean, there's actually some math here that we're kind of skipping. And then d minus lambda 2 of y equals 0. Those two cases, right? But this thing right here is really just looking like d y equals lambda 1 y, right? So this looks just like what we had before. So this is just y prime, right? So y prime is lambda 1 y, right? This one over here is dy equals lambda 2 y. So again, this should be looking a lot like, eigenvector. So it's like this is an eigenvector, this eigenfunction, this is an eigenvalue, right? But this is also just y prime. Okay, and we know how to solve these because here we just have y is what, e to the lambda 1 t, right? And over here I have y, let's call this y1 for lambda 1, right? y2 is e to the lambda 2 t, right? So these are two, if you like, eigenfunctions, right? Because d of e to the lambda 1 t is lambda 1 e to the lambda 1 t, right? So it has that property that d of something is constant times something, right? And then same thing with this lambda 2, okay? But okay, so these lambda 1 and lambda 2 are two linearly independent solutions for our differential equation. And so a linear combination of those is still going to be a solution, right? So if I take d squared plus ad plus b, plus b, okay, now, and I apply it to a linear combination of these, alpha, I'm going to just call it y1 and y2 for a second, alpha y1 plus beta y2, right? Well, this was d minus lambda 1, d minus lambda 2, right? Alpha y1 plus alpha y2, right? And so when you apply this, right, when you apply this one, it's gonna, kill off this second one here, right? Because I'm gonna get alpha d lambda y2 minus lambda 2 y2, and that, so that'll, because of this, that'll be 0. All right, so this will be 0 here, right? So the point is, once I have a solution, right, I actually can take a linear combination of those solutions and get another solution. And again, the theory kind of comes in and says that this has to be a two-dimensional space, so we need only two parameters, right? So this will give me all the possible solutions. So again, just to review the method one more time, right? We start off with something like this: y double prime plus whoops, I wish I'd stopped writing things wrong. Ay prime plus b equals 0. This is what we want to solve. We extract this thing called the characteristic polynomial, characteristic function out of this thing. All right, and so here I'm just using it. Yeah, I'm using this d for this. I mean, I've got in mind that these are differential operators. Basically, this polynomial, you factor this polynomial using, however you want to factor polynomials. All right, you take your two solutions that you get from this. Again, if there was a 3 up here, there'd be more, right? And so we're going to get two independent solutions, and then by 2 is e lambda 2t, right? And for your general solution, you're going to just take a linear combination of those two things. Good. All right, so that's kind of the method. Okay, so that's the method. So let's do it on a specific example. There's my example. So this is going to be like the previous one. This is going to be a damped spring, right? So again, it's going to be a spring, but now there's going to be some sort of damping. So here we have a mass spring system, and it moves horizontally again on a surface with friction, and the mass is attached to a spring. And here we're given the K, right? So K is 20 newtons per meter. And the mass experiences this damping friction with a coefficient of 8 Newton seconds per meter. If the mass is 2 kilograms initially, and is initially displaced by 10 centimeters, right, from equilibrium and release from rest, find the displacement function y of t. So, I mean, part of the hard part here is just the physics in some sense, right? So let's just sort of look at the physics, and I'm not going to even pretend to do a physics lecture, right? But the force given by the spring is minus ky. This is the physics part, right? So that's Hooke's law. And the force from the damping, well, that's the friction. And so that is told, it is minus cy prime. And now we're given k, right? We're given k and we're given c in this problem. Right, and then we're given also that, mass times acceleration is force. So mass y double prime, so this is the position function, right, is equal to force, right? And so here you have m y double prime, which is the force, is just the sum of those two things. So minus ky, this is where we're getting our equation from, minus cy prime, okay, like that. And so, and I guess that's really all there is to it. So now I just have to plug in the various pieces here, right? So this turns into 2y double prime plus 8 y prime plus 20 y equals 0, right? And so where did all these numbers come from? well, the K, the 20 is there, right? The spring damping coefficient is there. That's the 8, right? 2 is the initial mass, so 2 kilograms, right? So that's where all those things are. So we get this, okay? Now, in terms of solving this, we can clearly divide out by 2. So we can change this to this. 10 equals 0, right? Okay, good. And then next, so now we're going to look at this, right? So again, this is the same as this operation. So d squared, d plus 10, right? I'm applying it to y. That's going to give me that thing up there. It's 0, right? I just want to factor this now, okay? And for that, we're actually going to use, quadratic equation in this case, right? So we're going to get the root of this thing will be d. Maybe I don't want to call it d here. Maybe I just really, whoops. Maybe I really do want to just, we're going to take this thing that has a meaning. These are differential operators and just replace it with this polynomial. Sorry. All right, equals 0. All right, I'm going to find the roots. Okay, I'm going to get r equals minus 2 plus or minus I square root of 6. So that's what you get. And that's just from the quadratic formula. And we do get a complex number here. That's not surprising. We have a spring, so it's it's moving up and down and up and down. So there's like some sort of oscillation, and almost always when you have oscillations, there's complex numbers in the thing here, right? So, the point is like e to the I theta, right? That's just sort of the unit circle in the complex plane going around and around. So that's the idea. So our function then is y of t. Okay, now there is going to be just some sort of messy math that I think I'm not going to write all down here. I went and computed it ahead of time, but the basic thing is this. We're going to have our two coefficients. Instead of calling it alpha and beta, I call it C1 and C2 in this case. Our two functions, so here it's e minus 2, and the first one I do is minus I root 6 t, right? This is lambda, this is like, so I'm saying that's like lambda 1, right? And then plus, let me just get rid of this stuff over here. C2, oops, C2 e to the lambda 2, which is minus 2 plus I square root of 6. That's lambda 2 t, right? So this is our C1, just to make it clear, e to the lambda 1 t plus C2 e to the lambda 2 t, where lambda 1, lambda 2 are the roots of that characteristic polynomial, right? And then you just have to, find C1 and C2. Okay, so it's not completely trivial. So let's just rewrite y of t. So the e to the minus 2t I can pull out, right? So this is e to the minus 2t. You don't have, oops, gosh, just stop. E to the minus 2t, right? And then I have this C1 e to the minus I root 6t plus C2 e to the minus, e to the root 6t. I root 6t, right, like that. And then you have, then you compute y double prime. Okay, so here it is here, right? So y double prime, you just take the derivative, and you combine terms and stuff. So you get this thing for the derivative. And at t equals 0, you get this here. So you get y of 0 is equal to, let's just look at this. So here's y, right? Plug in y of 0. So this is 0 up here, 0, so that these both just become 1, right? So and this is 1, right? So y of 0 is just c1 plus c2, right? So that's y of 0. And we were given a displacement of 10 centimeters, and everything else is in meters, right? So we're going to say 0.1 meter, right? That's going to be our initial displacement. Right, and then you have y prime here, and so again, you're going to y of 0 is 0, right? So you're going to put in 0, so that's going to become 1, that's going to become 1, that's going to become 1, right? And so you end up with this stuff down here, right? So so y double, I'll just write it here. So this is works out to be minus 2 plus I root 6 C1. plus minus 2 plus I root 6, C2 equals 0. So that's what you get. So now you've got this system, right? So we don't really, don't really care about that. This is, 0.1, right? Just to make sure that's clear. We got a system of two equations and two unknowns, namely the C1. This is a y prime, sorry. You got the C1 and C2 you're trying to solve for, and you solve for it, right? And you get some solutions here. So let's see, the solutions turn out to be, now I'm cheating some, right? So it turns out to be C2 equals 3 minus root 6 over 60, okay? And C1 turns out to be 3 plus root 6 over 60. I root 6 over 60. If you look really carefully here, lots of things are coming in. Conjugate pairs, 3 minus root 6, 3 plus root 6, right? And so that happens all over the place here. And so if you think about that some, you can actually simplify a lot of calculations. And let's see, the other thing you can do is instead of using complex numbers, you can just stick to the real part of this thing. And so that would be giving you the sine cosine bits. Here you'd have to use the fact that, for example, I square root of 6t, right, would be the same as cos root 6t plus I sine root 6t. Right, so you're sort of moving things around from being, you're moving the complexity from one place to the other, but this isn't hard, it's just a little bit of work. And you get a final solution, y of t, right, using these two things. Actually, because things are coming in these conjugate pairs, when you get your solution, all the complex part goes away, actually, just sort of by magic. It's not literally by magic, it's because z plus z bar, complex plus a complex conjugate, is 2 times the real part of z. All right, so that's really what happens here. And so you get 2 to the minus 2t over 30. And then here I get 3 cos square root of 6t plus square root of 6 sine square root of 6t. So we get that solution. Okay. And if you wanted to, you could plot it and see what it looks like. And that's our damped motion, right? That would be fun to do. So it's a, it'd be a spring motion, but it would also be, damping, right? So it'd be going towards 0. So that's the idea. Okay, and then to finish the problem, right, you're really supposed to compute like y of 0.3, but I'll let you do that because that's just a calculator problem. Okay, again, just a quick review of the method. First, you have to get your equation, right? That took a little, that's where the physics is, right? That's where the application part is. And the way you solve it is you just take this and you sort of turn it into a corresponding characteristic equation. You find the roots, right? So lambda 1 and lambda 2 are these roots. The two solutions that you start off with would be e to the lambda 1t and e to the lambda 2t, together with some arbitrary coefficients, and then you use your initial conditions or your boundary values, initial values or boundary values, to compute C1 and C2. So that's the way these things work. Okay. Let's see. That's where I'll stop here. I'm going to redo this exact same problem using a first order linear system in the next video.